This quick video is about combining like terms, and we're going to take a look at how do we make equivalent expressions? How can we use combining like terms to make an equivalent expression? So first thing we have to think about are parts of a term. And once we understand how that works, then we can combine things or put things together effectively. So first of all, this is a term. This is what it looks like. And a term is made up of different parts. First, you have the coefficient, which will be a number in front, anywhere from 1 to whatever number you can imagine, positive or negative. Then you have the part that's the variable, and this would be the letter. So we have basically a number and a letter, or a coefficient and a variable. And the last thing that we don't always see, but you might run into sometimes, is an exponent. And that exponent would be the last part of the term. So these three parts, coefficients, exponents, and variables, they make up what how we look at terms. And our job is to look at terms and to put them together based on what is alike and what isn't alike. So let's kind of take a look at a couple problems and see if we can have that by definition. So here we have an example which says 3x plus 3x plus 4x. One of the things that we should be able to recognize is that if we look at each term, we see a coefficient and we see a variable of x, and we don't see an exponent because it has an exponent of 1 there. So when we look at these other ones that don't have an exponent, they all have an exponent of 1. So we can state that with clear conscience that this x to the first, this x to the first, and this x to the first are all the same term. We just have different quantities of them. So here on this first one, we have basically three x's, right? X plus x plus x. Here we have another three x's, x plus x plus x. And then here we have four x's, x plus x plus x plus x. Now, we can sit here and count them all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we see all together that we have 10 x's. This would be our equivalent expression for this particular expression. So 3x plus 3x plus 4x is the same as 10x. Now, some of you might be wondering about, let me erase, oops, sorry, I was going to get my eraser here, erase a little bit here. Some of us might be wondering, why did I pull out all the x's? Well, I did that because I wanted you just to see what was going on. But we can, in turn, just count the coefficients when the variable term is the same. 3 plus 3 plus 4, we can say is 10, and our answer is 10x. But remember, only things that are exactly alike can go together. So think of it like as if you were going to the grocery store. You see apples, and you see pears, and you see bananas. They don't take all the fruit and mix them all together. They kind of keep them in areas. So apples with apples, bananas with bananas, and so on. So, but in the apple realm, sometimes you see more than one kind of apple. You might see a green apple or a yellow apple or a red delicious apple. So even though they might all be apples, such as an x or an x squared or an x cubed, they may all be apples, but they're just a little bit different. And that little bit difference is in the exponent. So we want to keep an eye out for that as well. So that explains this problem. Let's take a look at another problem. Here we have 3 plus 2a plus 7. So I want us to think about which terms are alike. We can pretty much see this 3 and the 7. They are a number by itself. There is nothing else with it. And then we have the 2a, which has that variable as well. So we have two types of terms here. We have numbers that are by themselves, and then we have a number and a variable. So when we put together these two numbers, 3 plus 7, we would get 10. And then the 2a would just be basically coming along for the ride. Now, you could write it this way, or you could write it this way. And the reason we can do that is because of the commutative property of addition. Both of these, all three of these are equal to each other. They are all equivalent expressions of each other. Let's take a look at another one. Here we have 5 plus 2 times x plus 8. Now I'm going to address this a little bit differently because we're just talking about combining like terms and what things mean. So what this is saying is that I have 2 of x plus 8. So let me rewrite this. So basically I have a 5 plus, I need x plus 8 two times. So x plus 8 and x plus 8. So when I take a look at this, bring my highlighter out again, we know that the x's are going to go together, and we know that the numbers are going to go together. So we're going to keep things separate. So if we look at the x's, we see here that there's 1x, there's 2x's. So this would be the same as 2x. And then we take a look at the numbers, 5 plus 8 plus 8, and that would give us 21. So we would write plus 21. Once again, you could have written it the other way, the 21 first, and then the 2x afterwards. I have one more example we're going to take a look at, and then this video will be over. Here we have 3a squared plus 2a squared plus 2a. This is where I was talking about earlier. We kind of see something different. They all have a's, but two of them are a little different. These two terms that have a to the second power are the same. This 2a is not like that one at all. So what we need to do is keep them separate. It's like I said, it's like the apples. We have green apples and we have red apples. We're not going to mix them up. So we're going to think about these two terms here. And I see that I have 3 of them and I have 2 of them. Remember what this means. This means that I have 3a squares. This means that I have 2a squareds. And all together, we see that there are 5 of them. So this equivalent expression can be 5a squared. And here, it's just going to be plus 2a. Once again, we can have an equivalent expression by switching them because of the commutative property of addition. It can be 2a plus 5a squared. Hopefully, this short video on combining like terms can help you to make equivalent expressions.